So, here's our sound solutions. Sound is created by an object source. The object vibrates and repeatedly pushes the air. Those pushes are sound waves. So with the tuning fork or your say your voice box, you have this membrane and you make it shake back and forth. And shaking back and forth, and it's pushing out these pulses, and those are the little crests of the sound wave. What factors of a sound wave determine its pitch? Pitch only has to do with the frequency. Pitch and frequency are the same thing. What factor determines its loudness? Loudness is an energy thing. That's an amplitude. Sound wave has a frequency of 550 hertz. Find the wavelength. Now remember, for sound, the velocity is 343 meters per second. So if I want the wavelength, I know velocity is frequency times wavelength. It's going to divide both sides by the frequency. So the wavelength is going to be the velocity divided by the frequency. So 343 meters per second divided by 550 hertz. That makes the wavelength of that sound wave come out to 0.62 meters. If the wavelength were to be increased, would you hear a higher pitched or a lower pitched sound? Well, I know that velocity is frequency times wavelength. So if you saw a wave with a bigger wavelength, you would have a lower frequency. So you have a lower frequency or a lower pitch if we had a longer wavelength. If the amplitude increased, describe how the sound would change. Amplitude has to do with volume. So if I increase the amplitude, I'm going to increase the volume. It's going to sound louder. A scientist creates a sound wave in an unknown fluid with a frequency of 550 hertz. The wave has a wavelength of 3.5 meters. What does that make the speed of sound in the unknown fluid? Well, velocity is frequency times wavelength. So we're going to take the frequency of 550 hertz times the wavelength of 3.5 meters. So 550 hertz times 3.5 meters. 1925 meters per second. Why is it possible to hear someone talking in the hall despite the fact that there's a wall between you and them? The sound passes through the wall. It is transmitted through the wall, so it's going to change speed as it goes through the wall, but that sound is still going to make transitions from the air to the wall, from the wall to the air on the other side, and then finally to your ear. Why can nobody hear you scream in space? There's no medium in space. And sound requires a medium. There's no air. There's nothing in space. There's nothing to shake when you make that noise. It can't transmit that energy anywhere. Describe the principle of resonance and how it can be used in music, in instruments to amplify sound. So if a sound has a frequency close to the natural frequency of an object, The object will vibrate to. The object will vibrate at that frequency. As the object vibrates at that frequency, it's able to push more air and amplify the sound a little bit. That's what happens on a stringed instrument. Right? As you move the bow across the string vibrates. The bridge of the stringed instrument carries that vibration from the string to the soundboard, then the whole soundboard begins to vibrate, and that's what projects it. That's what makes high quality instruments so good. One small violin can pick up enough sound to be heard over the entire orchestra and fill the entire room because of resonance. Describe how a standing wave is created in a vibrating string. What 3 factors determine the pitch that you hear from the string? Okay, so a whole bunch of frequencies go to the string. The string can carry a whole lot of frequencies, but if the wavelength is right, then the standing wave gets set up on the string, if you have the right wavelength. So, if the lambda of a frequency is just right, if it produces, this is how we would say it, if it produces nodes at the end of the string, it will produce a standing wave, or it will resonate. And so the things that determine the pitch that you hear from the string, you have the length of the string. That's important. That's going to tell you where those nodes should go. And then you have the tension in the string. And then you have what the string is made up of, or we would say the density. Those 3 things sort of affect what's going on. And so for an idea of density, if you look at a stringed instrument, they don't all have the same diameter. One with a larger diameter has a higher density. That's all we're saying with that. Why does a middle C on a piano sound different than the same note played on a clarinet? It has different tones. In this, each instrument carries different resonating frequencies, different harmonics. So while the piano plays a C, that string is going to vibrate at different frequencies. And so you don't just get one vibration on a piano string. This would be sort of the main vibration that you get, but you also get, for the same length, different orders of standing waves that give you different pitches with the same thing. So notes that we hear on different instruments or in the human voice are not pure tones. They don't just have one frequency. They have multiple frequencies. They're all related. They're different harmonics that we can play on that. But it's those harmonics that give you sort of the tone of the instrument. So the piano can carry different harmonics than a clarinet can, even though they play the same note. That's why they sound different to your ear. Describe why you hear beats. They have nearly the same frequency, and this is when we get the beat frequency. So you have repeated constructive and destructive interference. It's like they're sending out crests and troughs at different lengths. So sometimes they line up and sometimes they don't line up. When they do line up, you get a loud sound. When they don't line up, you get a soft sound. And so the farther apart they are, the more frequently they don't line up. That's why you hear a wah, 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 wah when they're really out of tune. And when they are really close to being in tune, it slows down. It goes wah, wah, wah. And when it goes away, that means they have the same frequency. That's how we tune objects. Describe the Doppler effect. That's a change in frequency due to motion. So we hear the Doppler effect or see it. That's more of an astronomy thing. When the source, so that's the thing making the sound, or the observer, that's the thing hearing the sound, move. If they're moving towards each other, we get an increase in frequency. If they're moving away from each other, we get a decrease in frequency.